To live on the moon, we have to solve a series of engineering problems that don't exist on Earth. Our atmosphere protects us from most radiation and provides a stable temperature. On the moon, there is no air to trap heat or block the sun's rays. During the day, temperatures climb to 127 degrees Celsius, and at night, they drop to -173. Without the protection of a thick, insulating shell, any human structure would be subjected to extreme thermal expansion and contraction, eventually tearing itself apart. Sending materials from Earth to the moon is incredibly expensive. Current estimates suggest it costs tens of thousands of dollars to transport just 1 kilogram of cargo into lunar orbit. If we wanted to build a base using traditional materials like steel, concrete, or glass, the sheer weight would make the mission financially impossible. To stay there permanently, we must learn to use what is already on the ground. This concept is called In-Situ Resource Utilization, or ISRU. It means turning the moon itself into our hardware store. The most abundant material on the moon is regolith, often called moon dust. Unlike the smooth, weathered sand found on Earth's beaches, regolith is composed of jagged, microscopic shards of volcanic glass and rock. Because there is no wind or water to erode these particles, they remain sharp and abrasive. While this makes regolith a hazard for mechanical joints and spacesuits, its mineral composition rich in silica and metals makes it an excellent candidate for construction. It is essentially the raw material for a new kind of lunar concrete. Engineers are developing giant 3D printers designed to work in a vacuum. These machines use concentrated sunlight or microwaves to heat the regolith until it melts and fuses together, a process known as sintering. Instead of layering wet cement, these robots build up solid structures one thin layer of dust at a time. This allows us to create thick, vaulted ceilings and interlocking walls that can withstand the internal pressure of a breathable atmosphere without the need for glue or fasteners brought from Earth. These 3D printed shells serve a critical purpose beyond holding air. The moon is constantly bombarded by cosmic radiation and high-energy solar particles. On Earth, our magnetic field and atmosphere deflect these, but on the moon, a human would receive a lethal dose over time. A layer of regolith several meters thick acts as a heavy shield. Furthermore, it protects against micro-meteorites, tiny grains of rock traveling at kilometers per second. To the moon, these are essentially microscopic bullets. A thick regolith wall is the only effective armor. Energy is the next major hurdle. A lunar day lasts about 29 Earth days, meaning the night is roughly 354 hours long. During this period, solar panels are useless. While we could use massive battery arrays to store power for 2 weeks of darkness, the weight of those batteries would be prohibitive. For a colony to survive the long, freezing lunar night, it needs a power source that doesn't rely on the sun. This is where small-scale nuclear fission becomes the most logical solution for long-term survival. NASA has been testing a project called Kilopower. This is a small, portable nuclear reactor designed to provide a steady flow of electricity for years without maintenance. It uses a solid uranium core to generate heat, which is then moved by sodium heat pipes to high-efficiency Stirling engines. Unlike the massive reactors we see on Earth, these are about the size of a household refrigerator. They are simple, have few moving parts, and can be buried under regolith to keep the colony safe from their own radiation. Even with 3D printing and nuclear power, building on the surface is risky. However, the moon hides a natural solution: lava tubes. Billions of years ago, when the moon was geologically active, rivers of lava flowed beneath the surface. As the outer layers cooled and hardened, the molten interiors drained away, leaving behind massive, hollow tunnels. Some of these tubes are hundreds of meters wide, large enough to house entire cities. These underground cathedrals offer a pre-built environment with a naturally stable temperature and built-in protection from the sky. The first permanent moon bases will likely be a hybrid of these technologies. We might use robotic printers to seal the entrances of these lava tubes, creating pressurized transition zones. Inside, we can set up modular habitats and kilopower reactors to provide constant heat and light. By moving underground, we bypass the harshest elements of the lunar surface. Instead of fighting the environment, we are using the moon's own geological history to provide the foundation for a sustainable human presence beyond our home planet. Transitioning from short visits to permanent settlement requires a shift in how we think about engineering. We cannot bring Earth with us. We have to adapt to the physics of the vacuum. Through the combination of autonomous 3D printing, local resources, and compact nuclear energy, the Moon stops being a destination and starts becoming a home. These first outposts will be the proving ground for how we eventually settle the rest of the solar system, using the dust beneath our feet to reach the stars.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.